Hello everyone, I'm Humbo Yao, the first author of the article Experimental Study of the Permeability Evaluation of Coal with CO2 phase transition. I'm very happy to have the opportunity to be nominated by the Committee for the Best Research Award. Now, please allow me to briefly introduce the main work of the article. Energy demand has increased with industrial development. Although all countries are developing new energy resources, fossil energy still occupies a dominant position. Excessive combustion of fossil energy causes a sharp increase in CO2 emissions and the greenhouse effect. Therefore, the greater attention should be focused on methods to reduce the atmosphere CO2 content and achieve a long-carbon economy worldwide. CO2 capture and storage technology has attracted increasing attention and is considered to be the most effective technology to reduce carbon emissions. In particular, injecting CO2 into deep unminable coal seams can achieve the geological storage of greenhouse gases and increase the production of coal biomass, which greatly increases the economy of storage. However, after a period of injection, the injection rate of CO2 decreased significantly. Therefore, the laboratory research work must progress to find answers to the key factors that restrict the injection capacity of supercritical CO2, so as to realize the efficient storage of CO2 in deep coal seams. During CO2 geological sequestration, the supercritical CO2 pressure would decrease gradually with transport distance increasing, resulting in the change of CO2 phase state. The phase transition will change the density and velocity and have a greater impact on the injection capacity of geological sequestration. Therefore, the effect of CO2 phase transition on permeability should be considered. However, many previous experiments focused on measuring the endpoint permeability of CO2 injection into the coal at a different pressure and temperature, and investigating the changing of CO2 endpoint permeability with the change in the phase of CO2. These results cannot characterize the phase transition of CO2 distributed along the migration path of the coal sample, and its formation mechanics hasn't been studied to the author's knowledge. It's helpful to understand the change in CO2 injection capacity during CO2 sequestration. Thus, in this study, a large size coal samples were taken as a research sample, and 3 sets of gas injection tests were measured. Meanwhile, the change in core pore structure before and after CO2 injection was analyzed through long-temperature nature absorption tests. to reveal the influence mechanics of different phases of CO2 or the core pore structure. These experimental results revealed some key factors restricting the ability of CO2 injection during CO2 sequestration, and combined with the experimental results to put forward a solution to the field engineering. With the increase of injection pressure, the phase transition of CO2 from subcritical to supercritical would alter pressure distribution within the core, obviously reducing the internal permeability. For subcritical CO2 injection, the internal permeability decreases non-linearly along the migration path, and the maximum occurs at the inlet, mainly where the effective stress is smaller. However, for supercritical CO2 injection, the internal permeability forms a U-shape, and the minimum occurs in the phase transition region, where the effect is greater than its effective stress. Due to the presence of phase transition, a W-shape variation of CO2 permeability changes with the increasing pore pressure occurs. The CO2 phase transition would affect the core structure significantly. The pore volume of core reduced by supercritical CO2 absorption is 28.07%, larger than that of 2.63% for subcritical CO2. This change reduced core permeability by more than 63.3%. This study is meaningful to CO2 sequestration in deep core seams. In order to further optimize the injection progress for CO2 sequestration in core, based on the results of this study, two suggestions are proposed. First, since the permeability of the CO2 phase change ridge is lower than that of supercritical and gaseous states, the location of the CO2 phase transition can be determined based on the pressure monitored during storage, and then the permeability of these areas could be enhanced through techniques such as hydraulic fracturing, thereby increasing the CO2 storage capacity. Second, since the core permeability within the phase transition decreases rapidly with the increase in CO2 pressure, indicating that increase in CO2 pressure caused by the widely used continuous injection method may reduce the core permeability. Thus, absorption intermittent or impulsive injection at some pressure level would avoid the continuous increase of the CO2 pressure, which would overcome the permeability attenuation within the phase transition zone. The applicability of these techniques needs further research in the future. That's all. Thank you.